Great. So thank you, Sam, for the intro. And I will double on your comment. I am very happy to see the CCEM organizing such webinars and opening it to users in order to share our, our knowledge, our experiments that we do on the microscopes. I think we have a lot to learn between each other, and so I hope this type of presentation will become more and more common. The previous webinars also are very valuable that we also see from the staff, but I think that with staff and users together can bring a lot in developing novel techniques or just having more knowledge about what is possible to do at the CCEM. So just before starting, I just want to go a couple of disclaimers. So I'm gonna show today some strain characterization method, but I want to say that it's a subjective selection, even if I try to be objective. But I have my own biases, and so, like, of course, I won't be able to present all the possible techniques. Even some would be better in some context. And even regarding the references, I choose certain references that I feel that I personally prefer because I understand better. So probably this is towards my bias towards some certain authors that I prefer to read. It is not saying that the other work is not valuable, absolutely not. And I think that it's very important to explore all the possibilities that we have, especially regarding strain. I will focus on the CCEM equipment and capabilities. So specifically targeting the three, so Thermo Fisher microscope, the Titan high base, Titan low base, and the Talos 200. And regarding capabilities, so the Titan high base will have this probe corrector and image corrector. The Titan low base will be more targeted, so not really the image corrector, but more the biprism that we can use for holography. And for the Talos, it's more like this versatile microscope that doesn't have any correctors, but it can show some interest regarding strain characterization. Then the results I'm gonna show are, this was intentional, to show you typical results. So you're gonna see artifacts, you're gonna see some noise, they are not optimized. It's not the type of conference type results where you show your best of what you can get. So my idea is to really show the experience that you will have with the CCEM and their limitation for you to better address what you want to do. Like, the idea is for you to apply those techniques without like too much development, even if some of the techniques can be already complicated on the experimental part. And the targeted audience is like regular CCEM users. So obviously everyone is welcome, but I'm gonna use some acronyms that refers to the equipments. So like a regular CCEM user might follow the talk a little bit easier. Okay, so today regarding the content, we're gonna go through first a background because when we especially in the data interpretation of strain data, it's some elements that are very important to have before even just starting talking about strain in electron microscopy, transmission electron microscopy. So a bit of theory, we're going to talk about sample preparation briefly, and also the notion of method of technique, something that I particularly care of. Then we will dive into really the key topic, which are the strain characterization methods. And I'm going to go present 4 or 5 different techniques that we can categorize following like this schematic on the right. So you have, I will start with what is related to the high resolution imaging. So targeting like STEM corrected microscope or TM corrected microscopes, where you target high resolution, but you have often like a poor sensitivity. They are usually very simple. It's just imaging based, but then we have a very, very restricted field of view. And towards the presentation, we're gonna go to other techniques that are more complex, but they are targeting some other applications. So we're gonna accept to reduce a little bit the resolution to gain sensitivity. And so it will trade that in having a larger field of view. So depending on the application that you want, you will be going through this this arrow. And yeah, don't forget that the complexity of the techniques also varies. So even if you can have some interest on some of them, whenever, for example, we target some holography experiment, you have to be ready in dedicating some effort and time. So let's start a little bit with some background and a bit of theory. That is important. You will see why, because there are some key elements in the data interpretation that needs to be addressed. So when we think about strain in general, we just refer to continuum mechanics. And so you have here on the left like a schematic, just like just showing in general how we talk about deformation. So you have a body at a certain initial state. I'm gonna put my laser pointer that go through a certain deformation through time and goes to a certain final state. And it's the deformation through time. So we're gonna convert the geometry of the body at the end of the final state and compare it to the initial states and to find the deformation. So in continuum mechanics, we can have this infinitesimal description. So you have exactly the same graphics, but then here we can have like some infinitesimal approach. And with this type of description, we can use some like mathematical approaches, especially to use of derivatives, to be able to estimate the deformation. And I will come to those equations relatively often, where, for example, we're gonna have like first map the displacement field, so the change of position from one point to the other, and the variation of the displacement field will correspond to this. So the gradient of the displacement field tensor, this one is going to be related to our strain and rotation center as shown on the bottom right. So there are different ways of defining those elements. Here I just took like the most basic ones and accepting the small deformation approximation. But the general idea is that then when we go into the atomic scale, there are some comments that needs to be made. So first we are losing the continuum technically because we are like dealing with atomic columns. So here we have just to be a little bit cautious when using those derivatives. So the continuum mechanics equation is still applicable if we consider that deformation is small and there's no excessive abrupt variation. So in that context, this is not directly applicable, for example, for polycrystalline material, high entropy alloys, amorphous materials interfaces. So it's still okay to use it for single crystal. For other type of materials, there might need to be some adjustment, especially in the way we're going to describe the deformation here. So instead of having our continuum body, we can now have like our atomic description of this body. Through time, it's going to go through a certain deformation, and we're going to be using for example, the atomic column, the arrangement of the periodic arrangement of the atomic column as strain gauges. So here we can take, for example, in the initial state, one area that is going to be our reference, and then you compare to then in the final state to characterize the deformation. So on the right, you have here like the basic description, very common. So you will have in red here your reference that you choose. In blue, you overlap this with your unit cell that has been deformed. And by just making some comparison of the distances and angles, you will find the strain components, the uniaxial deformation, the shear, and the rotation. And that's very, very common and very easy to use. That's basically the idea. So having that in mind, we have certain problems when we talk about strain in the TEM. And usually the first problem that we have is that we don't have access to the initial state. So that is true when, for example, we have the sample at the end, it's already after all the processing, in terms of materials processing. So in here, the solution that has been found is to use a reference state already in the final state of deformation. So two cases can be here explored. The first one is to use a reference inside the material at the final state. So it is possible that in your final state, you have a part of the geometry that didn't undergo any deformation. Sometimes yes, sometimes not. But here, this is like since we don't have access to an initial state, we need to select a certain reference. The other option is you use a theoretical reference for the strain state. For example, just putting like the crystal structure at its relaxed state, and compare it to this theoretical reference. The problem with this approach, using the theoretical reference, is that now the calibration matters. While when you use, for example, an internal reference, the calibration doesn't matter. Often when we calibrate a microscope, your calibration standards are +1 to +1 or 2% regarding the level of precision. This 1-2% can be your level of strain into the material. So very, very often, we don't use a theoretical reference. We use practical and experimental reference that is inside the final state. And we're going to be talking about a relative strain characterization method when you use a reference that is in the final state of deformation of your material. So it's not that of a problem because in many cases, this reference is unstrained. But it happens that there can be some problems regarding the data interpretation. And let's see this very simple case, which is the silicon germanium growth on the silicon substrate. So the silicon germanium at its relaxed state has a higher lattice parameter than the silicon. So to be able to realize this epitaxy, to have this lattice matching, this layer on top needs to be compressed laterally to have this lattice matching. And then after the layer, gonna expand vertically. So that's the very classic growth by, for example, molecular beam epitaxy. So what we expect if we talk about strain is that we have a negative strain, like a compression in laterally. So this epsilon xx negative and this epsilon yy positive. The problem is that if we do this measured now using the equations that have been just shown before, like those ones here, now we have a different story, because if you measure the lattice parameter of the silicon germanium in comparison to silicon, we will find that laterally we have a zero. So like the very kind of shocking type of results saying that I have a zero strain, but technically there is a compressive strain. And that's the problem of this relative strain characterization method in the interpretation, is that we don't compare to the relaxed state of the silicon germanium, we compare it to the silicon lattice underneath. So this is very important to remember that the zero relative strain does not mean non-strain or no stress in the system. So this problem is coming from this reference, and it could be possible to overcome this issue by comparing it to a proper initial state. So in this case of this type of growth, what we would like to compare the silicon germanium is the silicon germanium layer, not grown on the silicon's lattice, but just at its relaxed state. So if now we do this comparison here between this red and the green lattice, we will find like the proper deformation state. The problem that is initial state actually doesn't exist. We are not creating the silicon germanium layer independently and compressing it after. So even if we wanted to have like this initial state, in that particular case, especially in molecular beam epitaxy, we don't have access to it. So sometimes it's not even like an idea to bother with this initial state. We just keep everything at the final state and use internal references to do our strain measurement. So, and then to make like the proper interpretation of the deformation. So usually we like to link it to a stress. So we can't use this easy, simple Hooke's law that we have. We have to make a small correction to take into account that the initial state is slightly different from the initial state from the silicon. And with that, it's then after all the interpretation becomes physical and easy to do. But this is something we have to keep in mind, because this happens every time, like all the time, whenever we do a relative strain characterization method. So this is one thing. Very important to keep in mind, and we will go towards through the presentation. The other thing that is important to keep in mind is the sample preparation. That has a huge impact, well, huge, like significant impact on the strain results. So here I'm just showing a classic flow of like a sample preparation using FIB. So this will be an in-situ lift out here. And for more details, I actually recommend to go to Travis' presentation, webinar on for the CCEM that will explain you in detail all the process. So I'm gonna just go to the key elements that will have an impact regarding the strain. So when we have to make an electron transparent tinfoil, that's the importance of the sample preparation method. So to do that, we need to first isolate a very small section of it from your 3D structure. So here there's going to be the lift out. So you take a small piece and you connect it to a support, like here a grid. And then we will do the finer thinning by creating those windows regions. So you can create one or multiple. Here the idea was to create multiple ones to have different thicknesses. And so the idea here is that you have generally this type of structures at the end. You have like a region relatively thick, micron scale thick. And you have in between a window region, so I'm going to call these pillars, and you have in the middle like a window region that is thin, roughly 100 nanometer thick. They're supposed to be electron transparent. So this structure is important to keep in mind, because it's going to be subjected to strain relaxation, because we have some free surfaces that are happening here. So let's see an example of how this is going to affect your strain results. So here I am presenting a very simple case. So a sample that I will use during the entire presentation and doing all the different methods I will be presenting. So this is here on the left the schematic. So this is a sample grown by molecular beam epitaxy by Sharam at the CEDT. So we have here the indium phosphide substrate on which is grown in indium arsenic phosphide layer, and on top an indium phosphide cap layer. So this layer in between is roughly 40 nanometer. So this system behaves the same as the silicon germanium sample just I described before, like in the theory section. So you will have your indium phosphide, here the lattice matching between the indium phosphide and arsenic phosphide, the expansion vertically. And then since again lattice match, then we have again a lateral lattice match between indium phosphide and indium arsenic phosphide and indium phosphide. And this cap layer should be the exact same strain state as the layer underneath. So this is what is expected on the right here. You will have like no deformation and no shear and no rotation at all. There is nothing that is involving in that. Everything should be equal to 0 in plane and in out of plane. So this should have a positive deformation because of this expansion that is estimated regarding materials properties around 2.4%. Keep in mind here, this is the 0 that we talk about. This is not a 0 stress in the material. This is 0 because this is just lattice matching, the relative aspect here. So that's why I put here relative deformation. So what is happening in coming back to our structure is that since we have some free surfaces all around, the free surfaces will relax the strain on the edges, and the entire structure is going to go a certain deformation. So you will see here the pillar regions are going some deformation, some bowing. So we are not interested in those pillar region. We are interested in this window region in between. So this is then after a section of that from this. And you can notice that there is no deformation along this 110 direction. So no displacement in that case. This is representing the displacement. This is a displacement map. Which is simplifying the problem here, that we have only like some displacement, some deformation going either along the 110 direction, which is the direction of the beam propagation, the lamellar thickness, and along the growth direction. So we can simplify this 3D geometry to this system. So here we have like an exaggeration of the deformation that is happening, and you can see here like the edges are bowed. And then after we will have like the beam that you're going to be crossing this 3D geometry. So sample preparation relaxes the structure partially, so we still have some strain inside. But the second part that is important is that the deformation is not uniform along the beam propagation direction. So this already can have some questions at what is exactly the beam propagation measuring inside, because we have a 2D projection of this 3D complex structure. But in any case, if we just look at on the simulation part, this is the result that we're going to be just keeping in mind. So as I told you, like the in plane along X, so perpendicular to the pillar, there no deformation, no shear, no rotation. And we're going to have this following notation towards the entire presentation. So we're going to be calling UX and UY the in plane growth direction, and UZ is going to be the out of plane direction regarding growth. The UX UZ is going to be our lamellar plane, the one we're looking when we do our TM imaging. And UY is going to be the beam propagation direction here, so the lamellar thickness. So along X, I just told you, no, at the 0, there is no deformation. So there is lattice matching. So what is interesting is to show what is happening along the Y direction, so along the lamellar thickness, and also in the growth direction. So the first result that is very interesting is to see this. We see here a positive deformation. This is saying that there is no lattice matching between the in-plane direction, so one of the in-plane direction with the substrate. This is the strain relaxation phenomenon that is appearing here. So as a consequence, this response on the out of plane direction, there will be a response here, because we don't have a fully in-plane growth here. And so you can see here that there are some contrast variation. That is, we don't have something that is uniform here. So regarding shear and rotation, still we will have some impact, but we're gonna neglect that for the moment. Well, we're gonna just focus on this out of plane uniaxial deformation here. So if we take, for example, some different line profile at different location of in the thickness. But this is what type of deformation profile we will see. So we'll have like a nice 0, then after something positive in the layer, and some things going on just at the vicinity. And that's the very important part here. If you look at what is happening, so the first curves that you have here are near the surface. The curves that are in the bottom are more towards the middle. And you can see that there is a quite non-negligible variation of strain, depending on where you're looking at the deformation here. At the vicinity, so here what we have, like, so indium phosphide cap in bulk, we are supposed to have a nice 0, and we can see that there are still some variation. Even here in the bulk underneath, some deformation is going negative. If you look at it towards the surface, some of them are going even positive than going negative. Some very different type of behavior regarding the deformation. So already here, from our expected 2.4%, in general, we will get something that is lower. And where it's supposed to be 0, we don't have a 0. So this is very important to keep in mind, because when we're going to do the strain characterization method and we would like to compare to simulation, it's a good practice to add this strain relaxation phenomena, because if you just go towards the simple models, you're going to pretty often be disappointed on the mismatch. So 2 conclusions from that. The strain in a tilde structure may not correspond to the strain in the original structure, very important. And also the strain results differ depending on which section of the tilde point is measured. So this is this notion of depth of field of a method. So this type of conclusion applies a lot whenever you have to do the sample preparation method. Of course, if you have a nanoparticle or sample that is already electron transparent, you will not be sensitive to that. But it is very, very common to use like those sample preparation techniques to look at the strain inside the 3D object. So yeah, we're gonna keep this in mind when we're gonna be talking about like the comparison, for example, between the different characterization methods. And last thing that I feel is very important, and not that mentioned a lot, is that whenever we talk about a method or a technique, we like there is a certain model that we are trying to follow, a physical model. And to follow this physical model, we're gonna set up some experimental condition, and to have the physical behavior we're looking for. And then we'll be using also a processing method that is supposed to properly address the model that the technique is describing. And we have a tendency to, for example, use the experiment independently from the processing. So we're gonna say, I'm gonna make my experiments the best I could do, and then I'm gonna do the processing after and do whatever I can do with that. The problem is that the processing methods have also some influence. So there will be some experimental data that will suit better some processing techniques. So depending on the fitting method you use, the Fourier masking, if you use a Fourier masking or not, depending on the algorithm or even the software implementation, there might be some interest in saying, okay, maybe I should change my experiment to suit better the processing method. And what is happening is that we have to accept some variabilities in the strain results. What I mean by that is that for example, you could try to compare your results to a publication, to something that is written in an article, and you find, I don't find it quite to be similar. My data is often worse, and so you may worry what wrong you are doing. And this type of approach, where you do an experiment that is adapted to a processing method specifically, this is what is changing from your data to be good to something to be great. And so it's not saying that there is anything wrong to do. It's just that there is an effect of the processing that will influence the way you're going to design your experiment. So this type of subject will should have be addressed completely, like in more generic manner. I won't go into too much detail about that. I will just comment here and there where those interactions matter. Okay, so this is what I wanted to say about like the background, just to have the idea. So regarding the interpretation, the relative aspect of the strain characterization method, forcing to do some jumps, like some tweaks in the interpretation. The notion of sample preparation that requires to have an electron transparent sample leading to strain relaxation, and this interconnection between experiment and processing when we talk about the technique. So now I would like to go like to the core of the presentation and present like the strain characterization methods that I find particularly suitable for the CCEM regarding like the equipments, and also towards our users, what we are trained to be doing, and what type of software we have like that is available in the community to be able to have like an experiment and a useful data at the end. So I will start with the high resolution imaging. The most simple thing, and probably most of you are already doing that. So the idea here will be just to do some final tweaking regarding your maybe design of the experiment, and then maybe just use what you have already to just process them and see if you get some strain information. So when we talk about high resolution, we have these two configurations, STEM and conventional TEM. I am very biased towards the STEM approach, the STEM corrected microscope, but like everything we're going to be saying is valid with conventional transmission electron microscopy. So what you have just in very briefly, you have a high velocity electron beam that you're going to be just either focusing or just illuminating your sample that is supposed to be thin. And then there will be some use of correctors, so probe corrector, image correctors to remove the aberration. So thanks to these approaches, we can have like some clean images that are representing the crystal periodicity. So again, we are gonna have here access to a repetition of a geometrical of some geometries that's gonna go under some deformation, and we're gonna be using this change of geometry to characterize our strain. So I just told I'm gonna be biased towards STEM, so I'll be just talking about that, but keep in mind that the CTEM also can have like the same kind of arguments. So here are just one typical example. Again, I'm gonna insist on this typical. This is not the best you can do, of course, but the idea again is to see when you come on the microscope and you have just a normal day, what you should expect. So here the Titan high base that is using the probe and image corrector. So the typical settings that you have here. Oh, and I just wanted to mention that if you want to know more about this STEM imaging, I recommend to go to Natalie's webinar explaining you how to align like those correctors. So the typical settings here, and it should be very familiar to what you're already doing on this microscope. So like 100 picoamps regarding the intensity, so spot size 910, a C2 of 50, semi-angle roughly of 20 millirad, nothing very special. A dwell time between 1 to 4 microseconds. So here this is some adjustments that will depend on the noise on the day. The number of pixels, so 512 to 248. There is an option to go to 4096, leaving like some huge data set. Can be used, but most of the time nobody is using it. But very important here, no CC correction. So like it's possible to turn the mono, to excite it, and to even get like the CC correction. It's just that the amount of work that is needed to do that, and to then after to convert to get like some nice imaging, I think is not worth it at the moment. Like regarding like the complexity in aligning the mono. So here we can already do some very good work without even considering the CC correction, the chromatic aberration. So here are some numbers, typical values that you're gonna get regarding like the different energy and the resolution you can get. And here again, it's possible to push more. This is not technically the spec of the microscope. This is slightly worse, but the typical results. So usually we're gonna go in 200 or 300 kV, and we're gonna get something around 100 picometer. That's the most of the cases whenever you finish with the alignment. So this corresponds to 4 or 5 rings of this gold sample that we use. Additional parameters to consider whenever we consider the imaging is the scanning unit, the one, so FEI, Thermo Fisher now, but FEI and Gatan, so they are different and they have different noise. So this can be useful regarding strain. And we have also access to different detectors, and that also can be explored regarding to the type of geometry that we want to use to look for the strain method. So yeah, typical imaging condition on the right, you have a silicon lattice. So you can recognize the silicon dampers. As you can see, there is some noise, there is some scanning artifacts that you can see on the top. Again, very typical. So what we can do from that? So what we want to just say in the theoretical section is that we want to use a geometry of reference, and then after see how this geometry is varying in space to determine our strain here. But then if we zoom in a little bit in those images, we can see that it's kind of difficult to say, okay, where is which geometry we're going to use and how we're going to identify the position of those elements. So here we will have a first bias towards going to the atomic column and say, okay, where are these located? And then after I'm going to define a certain geometry and follow how this geometry is changing. The problem with this all scanning noise and intensities instabilities, it's kind of difficult to say, where do I take the atomic column? Like here or there, depending on, if you, for example, use only the maximum value of the pixel, you might find some variation that are not compatible with the strain, like the strain measurement. There could be some other approaches here in looking at some areas that are not the atomic column, like for example, the vacuum between the atomic column here. So not technically vacuum, but like some areas with lower intensity, because actually it doesn't really matter on which type of geometry you take regarding strain. Whatever you have the nicest geometry where you can define the vertices of the geometry precisely is going to be the one that give you the best results. But here, like, yeah, we have a problem with noise that makes it a real challenge to localize the vertices of the geometrical structure. So the first idea here will be to try to reduce the scanning noise. So a couple of strategies here that can be actually used in a complementary manner. So the first one is you use a low dwell time. Usually when you're reducing the dwell time, you have like the scanning noise is less prominent. Data filtering that still applies, for example, some Fourier filtering, and also the multi-frame approach. And I'm gonna just go very briefly towards this multi-frame approach because I see that not enough users are maybe using it on the tighter high base while we have the capabilities of using it. So the idea is to use a short dwell time and fast acquisition process of image series, and then let a software dealing with some processing, which is called like the rigid registration and non-rigid registration, that's going to be applied to correct the sample drift, but also some scanning instabilities. That's very interesting because like from we have here a kind of a plan to be able to remove that. And the possibility of doing that is just coming from the fact that you get multiple information that is all going to be slightly different from each other, but that are converged towards one hypothetical unique solution. That's the general idea. And also in this short dwell time and image series, we have usually a slightly higher dose accepted. So when you have a beam sensitive material, this also strategies can help. To know more about these methods, I recommend these two articles. So this one, like mostly mathematical. This one, well, both actually mathematical, but this one is more adapted towards this Smart Align plugin that has been developed by Lewis Jones. And we have actually access to Smart Align in digital micrograph in the Titan high base, and I really, really, really recommend to use it to improve it, especially to remove the scanning instabilities. There is also the drift correction also element in the Velox. I don't remember the name of it, but also something that is relatively easy to use, and I really recommend to use it. So here you have an example of so in-gas on AlGas, so quantum wells. And on the left, you have like the classic type of imaging, exactly the same kind of parameters as on the silicon dumbbells before. And here I just put like this temperature type contrast just to highlight better the noise profile inside. And on the right here, you have an image series of 50 images and with Smart Align. So this is all taken on the gate and IDF with a dwell time of 1 microsecond. And so here, like by eye, it's clearly, yeah, we have a net improvement regarding like the noise. To be fair, it's not fair to compare these two images because the dose is completely different between both of them. But like in whatever case, regarding like the comparison we want to make between like the two experiments, what matters is that we have something that is the cleanest possible. So at the end, I personally feel that using this Smart Align plugin helps a lot in removing these scanning instabilities. And I don't have any like particular take on this Smart Align plugin. I just targeting the solutions that helps the most to get the best experiments here. So by using this, then after we have like this a little bit cleaner images. So now we are coming back to this black and white, so grayscale contrast. So as you can see, like this, that's also an interesting part. Like wherever the color scheme you are using, it seems to be slightly worse compared to the previous case, but this is exactly the same image. But once we have this type of images, it seems to be better now to be trying to localize those atomic columns and to define those geometries and look at the variation of the geometries to find the strain. So here the approach will be say, okay, let's take, for example, the maximum pixel intensity and see how it goes. And this is an example here of a line profile taking along this periodicity here. You can see that we have a nice definition like for regarding the profile here, and we can say, okay, let's look at the distance between these two maximum pixels here. And we have, for example, here 29 pixels. Everything seems to be fine. So now let's imagine that there is a strain here, that we have, like, for example, a displacement of that atomic column of 1 pixel, like the minimum thing that we'll be able to see. If we just make this strain measurement, like this 1 pixel over 29, it happened to be a very high number, 3.4%. So the strain sensitivity on the imaging, on this even high resolution images directly is clearly not sufficient. The discretization process is here our problem. So it's absolutely mandatory to have a sub-pixel fitting method if you want to be able to characterize the strain to an acceptable sensitivity. So this is what is coming like next, that you have then after this processing that is happening. And the processing will have like a direct influence on the sensitivity of the strain results that you got. And here we have a variety of options to determine the subpixel position of the atomic column here. So center of mass, 2D Gaussian, sinusoidal function, polynomial function, whatever type of function we can see. Some other very interesting, like the template matching one, the looks for the correlation. And there are actually some solutions that already exist regarding that. So the one that is called peak pair algorithm, PPA. This is a licensed DM plugin. And here Atomap, an open source Python package, here that you will see some results on the right. StatStem, that is another open source software based on MATLAB. So there are some solutions that exist. Probably there are some others, and we will see like actually in articles, some people also doing their own custom way of finding this position. So, and this becomes absolutely mandatory to do that if you want to reach the sensitivity like let's say 10 to the minus 3, for example. So you have on the example on the right of this quantum well picture that I just used before. You can see here like some process using Atomap, and you will see here that the position that has been found here, and automatically, like, I didn't do anything special. I just went through the basic tutorial and just let it go on this picture after the smart line alignment. And Atomap is using the 2D Gaussian approach to do the subpixel fitting. So that's looks great. Just one thing to keep in mind is that with lots of atomic columns to fit, the processing can become very slow. So on that entire image that I just showed before, like you can just this one, you can estimate quickly to have like 2,800 numbers, so 5,000 peaks, more than 5,000 peaks to find. And this is kind of slow. So like just in this example, I just took a smaller field of view to have something that is acceptable. So like we can hear, like you can already feel that there's going to be some limitation regarding the number of atomic columns that you can have in one set. So here, this is just then after I wanted just to push one step further regarding Atomap and try to look at the strain results regarding this process here. And you have here like the line profile. So technically, there was expecting to have no strain. I don't have actually that much sample myself with such a small scale, like nanoparticles or something like that. I usually work with like a bigger type of devices. So this was the only example I had in mind. So this one, unfortunately, has no strain. But you can see that there are some artifacts appearing. So this is on the other interface. This seems to be like a big dip. So maybe there is a little bit of strain here. So what you measure here, this intensity is the number of pixels that is separating the two numbers. So this was around 23. And here is a little bit of variation. So like here to really conclude like about the strain might be a little bit difficult. But as no strain was expected on that, I wouldn't consider it as to be a measure here. It'll just be part of the noise. So here, just to show that you can have some strain regarding this using this type of method, I just put an example here that is using the StatStem process on a nanoparticle. This is an open access article, so and I recommend to read. So here, this is the type of results that has been optimized, really pushed to the limit. So the amount of work to do that is probably huge. Because this is a 3D atomic reconstruction of this gold nanoparticle, and then after they took some different section of it and measured the strain using this type of real space approach. So probably difficult to do, but like what is interesting to see is the scale that we have, that is relatively large, kind of saying that the sensitivity like is not as great as what is could be with other type of methods that are going to be presented later on in this presentation. But yeah, this type of things are possible to do, and I think that even if you have already acquired some high resolution images, there could be some interest in just trying to process them using those methods to see what you can get from them. But that's the idea. But what is happening there if you have like some slightly larger devices that you don't have like just nanoparticles that have like a couple of that you can even count the atomic columns. What about you have like, for example, this thin film, this sample that we're just talking about, like we presented when we're describing the sample preparation here, that has this 40 nanometer in thickness here. So because of the size of it, we need to reduce a little bit the magnification, and by reducing the magnification, we affect here the sampling scheme. And now before we had 29 pixels, now we drop to something like 8 pixels in this type of images. And when you have an aggressive sampling scheme, the real space fitting method now start to really struggle because there are just low number of pixels around the features. It makes it difficult to find it. Also, in addition, the more you reduce the field of view, the more you increase the number of atomic column. So it looks like this real spacing method are not very suited for this type of data. Where you're still in this high resolution mode, but slightly larger field of view. So I would say that to like limit this type of approach to small structures like nanoparticles or narrow field of view. But those layer type can be still processed using the geometric phase analysis approach, which is based in Fourier space. And here, instead of looking at each individual atoms, the idea is to decompose your signal into like in Fourier space to know and have a more global view of like how those geometries are varying in space. So I will really recommend to go to the original paper of that is really well written, and I find also easy to read. I'm just gonna go through very briefly to the key concept. So here, the first thing is that since we have a periodic lattice, is to use this periodicity to decompose in Fourier series. And that is a graphical illustration of this decomposition. So you have this atomic arrangement, you take the Fourier transform of it, and you will find some dots here. And each of the dots represent a different families of periodicities. So you will find here, for example, the 004, the 220 in red, and so on. And then after by this one images is decomposed into this set of individual periodicities. So what is interesting in this GPA approach is that include the small deformation in the Fourier series decomposition. So it's technically not correct to do that because we are breaking the periodicity here. But if the deformation is small, we can accept that this coefficient that is supposed to be constant to vary with space. And this coefficient has a real space and an imaginary component. And this imaginary component would be this extra phase that's going to be related to delta G. Delta G, that is going to be our variation of the G lattice here. So it's possible to transform it to have, if you prefer, to have U, which is the displacement field here. So then the idea would be to say, like, since we have this type of description, is to say, okay, let's isolate, for example, different lattice family to try to extract just this phase component, because with and try to see if we can see the variation of them. So this can be done by taking Gaussian mask in Fourier space along one reflection, and then this isolated frequency come back into real space. We'll have a real space and an imaginary space, imaginary component, and you just display the imaginary component here by looking at the phase. And we're gonna choose an area that is gonna be, say, a strain. So coming back to this definition of a relative strain Cartesian method, defining of a reference, internal reference in the final state, that will put G equals 0, and we will have here the view of the delta G, variation of delta G through the entire image. So with that, with these two phase images, we can, by taking the gradient of this phase, having a direct access to delta G. So this is again an approximation, because when you do the derivative of this dot product, we don't have directly delta G. There is an approximation. So this is this no abrupt variation hypothesis that is important to have. As we, during the masking process, since we select a certain reference here, we have also the evaluation of the reference, the G component in the 2D space. So once you have these two matrices, you can then after estimate your gradient of the displacement field and find the strain in the rotation in a similar manner as we just talked before. But here, like, the equation is not using directly the lattice spacing, but just the evaluation of the G vectors around on the entire image. And that's the very key difference between GPA and these real space methods. So what we gain from that is that we don't have an individual evaluation of the geometry variation. Now we have like a phase component that is measured at each pixel of the image. And this is what we get here from this indium arsenic phosphide sample. Again, we're going to be using this sample all along now. And as expected, we have no deformation anywhere, just in deformation along the growth direction. One thing I didn't mention is that whenever here the image is rotated by 90 degrees to align the growth direction along the horizontal scanning line here. This is because the noise profile is preferential in that direction than in out of plane direction. So we have a tendency to align the direction of deformation where we expected towards the in plane direction. So that's why I rotate this to limit the scanning noise. We can actually see the scanning noise here, as you see. So if you rotate the image and you invert X and Z, you will have on top of that this noise profile on top of this. So regarding the processing of this, there are multiple solutions available. So the GPA plugin for digital micrograph, this is licensed, so you need to pay to have access to that. I developed an open source Python package that is going through that. Like it's not the most well written, but it will do the job. There are some other packages, free open source, Strain++, that is an open source C++ package. Another one, DM plugin. So there are some solutions because GPA has been used for so long that there are some people that are providing some solutions into processing the data directly from your high resolution STEM micrograph. So one comment here about this GPA is that, and we have like something like particular that is particular to GPA is the link between the mask that you use and the noise that you get in your final results. So if we just go like very simple, it's actually not that very accurate what I'm saying here, but just to go very easy, like when we, for example, do a Gaussian masking around the reflection, we multiply by a Gaussian function. If we come back to a real space, then this product becomes a convolution. So as a first approximation, very quickly, what we're doing with this Gaussian mask, we do a Gaussian blurring of the image in real space. And whenever you do a Gaussian blurring, we have the tendency here to average the signal in this Gaussian region. And interestingly, when you, for example, change the size of the mask, so large mask to small mask, you will see that the noise level is going down. So you will have like a better sensitivity with a worse resolution. So, and you can see that these are the line profiles taken along this growth direction for different type of averaging profiles. So here, 1 time the resolution, 3 times the resolution, half of the field of view. But just general idea is that you have better resolution, worse sensitivity. And this seems to something that seems to be absolutely weird. Why would this completely change regarding the size of the mask that you are using? And this is related to the noise that you have in your data. The fact that you have noise and you are using this type of Gaussian blurring, the Gaussian blurring helps into averaging the noise that you have. And this is something that this is specific to this processing method that we are using here. Something that we didn't have in this real space method just before. And here we have this interconnection here coming between the experiment and here, because if there were no noise, there will be this Gaussian mask will have absolutely no effect. And so here you see here that is the first key in trying to improve your data based on the processing method that you are using. So something also to keep in mind when using the GPA. So that will conclude like this high resolution imaging. So usually the type of resolution that you have is like a 1 unit cell to a few nanometers. You can target to a sensitivity up to 10 to the -3, which is already relatively good. The strain maps are directly from the STEM or the TM images. There's no extra setup into that. So you just have to follow this. And the GPA is also that is massively used by the community and used as a reference method even. So when you develop a new strain Cartesian method, you usually compare to the GPA method to show its proof. Two important limitations. So the scanning noise in STEM, that's definitely like affecting the sensitivity of the method. So there are some approaches, the multi-frame that we just talked about, to help it on that. The second one is the field of view, and that is coming actually directly from sampling. This is a very important thing to keep in mind, is that regarding to sampling theorem, if you have a certain resolution, this is defining you a pixel size that you can use to satisfy the oversampling condition. And this is like shown here. You need to have the pixel spacing that is smaller than half of the resolution. If you get into this higher pixel size, you're going to be undersampling. And the undersampling will cause some irreversible distortion of your signal that will completely change your geometrical structure that is not representative directly from the crystal lattice. So here, this is something like, again, to keep in mind that when you do this high resolution type of imaging, you can't go to a larger field of view automatically. Okay, you will need to find a new strategy to cope with that. So that's for the high resolution imaging. Now we're gonna go towards diffraction interferometry. So the idea here is to break this field of view limitation. There are some nice high resolution images now that can't go to, for example, 1 micron or 2 microns. And here you have two different approaches to break this with different strategy. So we're gonna start with diffraction, and the idea is instead of measuring the deformation from the crystal structure directly, the idea is to take a signal that is representing the crystal structure, but that can be averaged on a large area. So, for example, in this case here, you will average, like, instead of taking the direct image of the crystalline periodicity, you're gonna take the diffraction of it. So here, for example, by putting a pixelated camera on the bottom. And now what is happening is that you have a certain probe that is going to be averaged the deformation around a certain area, and then we're going to get the diffraction pattern of that is a direct representation of your crystal periodicities. So here we have the diffraction recording in the indium phosphide, zinc blende type of structure. And so you can identify the peaks. We can also index them. And how we look at the strain in this type of structure is that to look at the variation of the G vectors. So this is just an example here. You have the G220 here. And if there is some deformation, this dot will move. So in this case here, I just put it on a little bit further. So let's imagine this case when you have the G that is bigger than the previous one. This will mean that the despacing is actually shorter because there is an inverse relation between the G and the distance in reciprocal space and the distance in a real space. So by looking at the variation of the position of the diffraction spots, you can find the deformation because this is a direct representation of your crystal lattice. But the gain here is that we are not limited now in imaging one unit cell. You can image a couple of unit cells at once, or you can even move the probe at completely different location. So we are not bound in having this oversampling condition now anymore. So by breaking those, this is like the two mode that I propose to use for diffraction for the strain application. And these type of elements are found in beam settings whenever you are on the Titan high base or in whatever Titan high base, low base, or Talos. And there are two modes that are specifically targeting, which is micro probe stem and nano probe stem. The difference between these two modes is that you have a different convergence that you have. So what you want is to have either a stem probe that with the disks that are not overlapping with each other. So you want them to be isolated to be able to identify their position and measure the distances and angles between them. In those type of settings, so usually what you want to look at is to have a small C2. That's the first thing that you're looking at. And then after, depending on the micro probe and nano probe, you will have like It's what we call the high semi-convergence angle in terms of strain, 1 to millirad, which is still very low, and the low semi-convergence angle in this microprobe, which is very small, more than 0.5 millirad. As a consequence, we have two types of resolution. The microscope will be like poorly resolved, but will have like a nice, well-defined spot, very small spot, while the nanoprobe will have this 1 or 2 resolution, better resolution, but a more spread beam. And then based whatever mode you are going there, you just have to acquire a diffraction map or line profile on either the CCD or a direct electron detectors like the K2 that we have on the Titan one. There's no need to have any beam stopper. Usually we go with a high spot size to reduce the intensity, and usually also a low acquisition time, so 100 milliseconds for CCD. And then depending on the level of sampling you want to use, usually use 5 to 1024 pixels for each diffraction one. So this is here what we're related, you might be more commonly referring to for the STEM method. You acquire a diffraction map of those you acquire a map of diffraction patterns, and then you will have to process them to find the strain. Important here is that you have two types of different diffraction that might be targeting two different processing methods, because they are not exactly the same here. And the same thing as in before, if you just limit yourself by finding the maximum position of the peak, your sensitivity will be too poor. It's going to be slightly better than in comparison to the real space method, because you can play on, for example, the camera length to space the spots in different distances. But in general, you want to add a subpixel fitting method to determine the position of the diffraction disks or spots. And so again, we come to the same area where there are lots of different solutions. Center of mass, 2D Gaussian, template matching, edge detection, or you can even make a seabed simulation and try to overlap with the pattern that you have. So and each of these solutions will have like slightly differences. And again, this link between processing and experiment happens. You will not process the two type of profiles here in the same manner. Here, I just wanted to show like a very nice work actually. Like, and I think this is like really like a groundbreaking. It makes it available for everyone. Like this Pi4D STEM package. That is so I here focus only on the strain aspect. That is using like a template-based matching, but also some more complicated mathematical approach to make this Bragg disk position detection. So you have the diffraction data. This is how they here like a map that is just showing that the detection of this Bragg disk, and then after they will convert that into this type of maps where you have only like single points that just representing the location of those disks. And then in the similar manner as what we were doing in this high resolution, you will define the geometry here. So these are the two arrows here, that an initial geometry, and you will see this change of geometry on all the different diffraction patterns acquired on the map. And you will see exactly in the same approach. You will use the G reference that you will, for example, take from one selected diffraction pattern. Then after you measure the G or the delta G, depending on like what you want to measure on those maps. And then by using this, again, matricial approach, you can find the gradient of displacement fin and then find the strain and the rotation tensor. So a very elegant piece of work. And that's also open access article that they are providing an open source package. So like, I think here there is definitely some more work to do in trying those packages that are made available now. I just wanted to mention that there are some other solutions that we have, like the PyXM is an open source, also open source Python package that is also dealing with diffraction. I'm not sure if there is a direct relation to strain mapping. There is, but there are some Bragg detection system that can be used to then after calculate the strain. We have a term official license software that is called Epsilon that is available on the offline Velox version. I didn't try it. But I know that this can be a very interesting software to use for looking at strain. And there is also the Gatten license strain module that I actually used, and I'm going to just show you an example here. So we come back to the same sample, indium phosphide, indium arsenic phosphide, and indium phosphide, the same thing as we are talking from the beginning. And here the experiment was designed to just test the K2 in situ mode. So I didn't spend time in optimizing this data. Again, I come to this saying like typical results that we're gonna get. This is definitely possible to do better. So this is on the Titan high base. Using the StemX scanning unit and with this in situ mode that is with this 400 frames per second. Just a couple of numbers just to make you realize how big this data is that if you combine, so I couldn't do the binning easily in this type of settings. So I just took the full CCD here. Like you see the number of pixels is huge, while the map is relatively small. And this is already 8 gigabytes of data. So, but there's definitely some improvement to do here, spending some time. And I use here the GAT and strain module processing that is using a center of mass approach to get those. So since it's not open source, like I don't have exactly all the details on that, but this is what I've been told. And the total acquisition time for the entire map is actually a few seconds. It's amazing how fast this goes and how fast you can generate some gigabytes. And here you will have like 2 examples of those diffraction patterns. So here in the indium phosphide, in the indium arsenic phosphide, you can see that the intensity distribution is not uniform. So it might be questioned like, is the center of mass really the best approach in trying to find the position of those disks? So, you know, like here might be some thoughts, and we'll definitely have to try the Pi for the STEM module to see how this goes with that. But this is the strain maps I obtained with this sample using their approach. So epsilon x, epsilon zz. So supposed to have 0 everywhere and just have a positive deformation in the indium arsenic phosphide layer. Kind of, there is still a bit of noise. So this is try to explore. I am really thinking that this is coming from the center of mass approach, that this noise contribution here that could be improved. Then as I talked that the diffraction can improve the field of view. So this is just another map to see that we can go like higher in field of view, so more than 200 nanometers here. Well, then after you can go to a micron level. This will depend on your scanning coils and the distortion that you will get in your image and how far you can go. But this is like, again, a typical result that you can get. This type of maps, again, 5 gigabytes in a couple of seconds. So definitely you need some like big hard drive into looking at those data. And we will find like, so regarding the values, something around 2%, a bit low. So again, try to see some more work needed, but definitely possible to do diffraction at the CCEM. One word before I finish on the diffraction technique is the use of precession, because like especially in the strain context, has been showing some great results. So the idea of the precession is to rock the beam by describing a hollow cone shape. So you have on the left an animation of that. So what you have here, a normal diffraction. So you just like collect the diffraction on your CCD, and now you can tilt the beam in a certain manner, and use a D-scan to compensate this tilt, and then make your beam describe this circle, so that it will describe this hollow cone. So you are exciting some different orientation of your like diffraction at the same time. And if you can imagine this, actually the precession mode is done very fast, like 100 hertz, 100 rotation per second. So what you collect at the end is this new pattern that has a different intensity distribution because of this different beam tilt excitation. And you have here an example that is very like speaking example of what the precession is bringing. And again, this connection between experiment and processing. So you have this here nanoprobe mode here, and what you can see, so I think this was done on silicon germanium, and you can see some features inside here that you have here. So 1 nanometer resolution and 2.2 millirad semi-convergence angle, and this is with precession off, and this is with precession on, and you can see how the intensity changes, the intensity distribution changes inside the disk. And probably here the strategy to do the processing will be different. So in here you have also like a better more spots that are illuminated, and also the intensity that is more uniform. And so like it's not, of course, like on the processing, the world is huge, like so there's probably some great strategies tackling that. But I have the feeling that using the precession method make the processing method easier on that type of here. And what is very interesting is that there is no loss of resolution in that aspect. The same thing can be applied into this microprobe mode. So like a little less convergence. So it's probably still nanoprobe. I'm not totally sure about this experimental condition because the resolution is slightly small. But the idea is to say that the precession is not degrading the resolution. And on the right, you have like this wonderful map. So this work has been done in CEA Grenoble. They are using like Titan's microscope to do this experiment. And here, this is combining 2 nanometer resolution with 0.02% precision. So the sensitivity, you can see how gorgeous those strain maps are. And this is combining this effect of precession with the strength of a processing method to look at those disks. So what I want to mention is that the precision hardware is available on our Titan microscope. We have the option of doing that, but we have no license to use it. So if there is anyone motivated to using that, to have this precision, maybe we can convince some people in buying those options, especially that the precision can be also used for crystal orientation mapping, not only for strain. So something maybe to look at as a potential future development. So this is here my conclusion regarding the diffraction method. So in brief, you get something like about 1 to 5 nanometer resolution, sensitivity down to 10 to -4. Also, this is dependent on the setup and the processing method. So this might vary 10 to -3, 10 to -4, but usually 1 order of magnitude better than what you get into high resolution imaging. The field of view, 10 nanometer to a couple of microns. So then after we have to think about the scanning coils, because at very large field of view, you have a very nice disk alignment, and also you might have some distortion that can happen. It's a relatively simple experiment. Like you just have to click diffraction, and then after record the diffraction, there is a little bit of small setup, but there's nothing like really complicated that I wouldn't see any regular CCEM user doing that. And we have also a semi-automatic processing that is so like not that complicated to do, I personally feel, and applicable on all microscopes with similar performance. So here, this is a great tool, for example, to use on the Talos directly. When you have the Titans that are heavily booked, especially the Titan high base, you can go to the low base, onto the Talos, you will have the similar performance. The only difference is that on the high base, you have the K2 that you can use, but like the K2 does not bring only advantages. So especially in going in this in situ mode, this requires some change of cables and everything that is not that easy to do. So sometimes if you want just to do a quick diffraction, you can go on the Titan low base, on the Talos, and you will have like similar performance. Regarding the limitation, huge data set, as we talked about, like gigabytes in a few seconds on the K2. So then after you need to have like a very efficient processing method. Just to open the data is already a challenge. And then after, I would say just the diffraction methods are just not enough developed at the CCEM. That's actually our stronger limitation. Regarding what is available right now regarding diffraction, especially regarding softwares and just like what the microscope can do, I really think that if you are a regular CCEM user and you want to do some straight, this is the go-to method, especially if you don't find your high resolution imaging like not satisfactory. I will definitely consider like this diffraction method to go there. So then just to continue, so we're gonna go in a higher level of complexity now, and have like another strategy to increase the field of view, which is this regarding looking at the Moire interferometry and holography approach. Those are start to be very complicated, and I would say that if you want to use them, there needs to be kind of a justification, because usually you're going to spend lots of time just in setting up the type of experiment, and the processing usually is kind of a little bit more complex, but worth to be approached. Regarding that, the general idea is that whenever you consider like a Moire interferometry experiment, you consider the interference between 2 or multiple waves. And like here we have an example of 2 waves that you bring into interference, and you will have a very generic type of equation like that. When you have like this cosine QX plus theta, there's like an oscillatory component. So what is theta here is the difference of phase of these 2 waves. So this is the use of holography, is to reveal the phase, like the phase difference. This is the main purpose of using it. But you have this other component, which is the carrier frequency. That is actually the difference of the wave vector here. And this is something that we don't really put much more attention, but this is actually the argument that is used to increase the field of view. Because like if you make a smart choice in this K1 and K2, you can lead to a Q element that is of orders of magnitude different from K, especially if the K are close to each other. And that's the idea of increasing the field of view. On the right, you have this schematic. So you have the overlap of 2 periodic elements with slightly two different wave vectors or periodicities. So this will be the inverse regarding the wave vector. And if you overlap them, you're going to generate some Moire fringes just by considering the overlap that has a different periodicity that is related to this. And as you can see here, the periodicity of both is small and this periodicity of Q is large. And that's exactly what we're going to be using. We're going to be trying to use to expand the field of view by using these Moire fringes instead of using directly the fringes from the wave 1 and wave 2. So I'm going to present two methods. Stemware Interferometry, that's my research topic. And here, I would say that easy to set up experimentally, difficult enough to process. And then Darkfield holography, this is just like to finish the presentation. Like this is maybe like the creme de la creme of the strain calculation method regarding the sensitivity. But the complexity regarding the experiment is huge. So yeah, but you will see by yourself during the presentation. So let's start with Stemware Interferometry very quickly. I don't go to all the details of that. I just try to give an intuitive approach. And I will really advise to go regarding the articles if you want to know more. But the idea is to make an interference between the crystal lattice and the stem sampler, because these two elements are periodic. So if you choose a sampling periodicity that is close to the lattice periodicity, you will be exactly in this configuration as described before. Wave 1 sampling, wave 2 the crystal lattice, and we generate some more fringes. So if you look at more on the signal processing aspect, so this is, for example, your sinusoid function that is representing your original function, a crystal lattice. Those here in black, those are the point of measurements, your delta function that you put there. And you see that your delta function seems to be following another type of sinusoid. This is the one that we call the Moire fringe that we get from that. So in signal processing, this is called an aliasing artifact from undersampling. And here in the community of physicists, we call this Moire sampling because we overlap the sampling with we do the interference of the sampling wave with the crystalline lattice wave. So if we relate to the previous part of the presentation, we just talk about this. We say that we have this largely oversampling stem micrograph that we're doing in high resolution imaging. We're saying this was great, we can use it. And then when it was undersampled, we couldn't use it, saying that because we have a distorted like the sampling is the undersampling condition is distorting the crystalline lattice, and we cannot recognize the silicon crystal structure, for example, in this example here, which is clearly the case. And that's the objective here. The Stemware Interferometry is making use of those undersampled micrograph to find like the deformation inside this. So it's the transition is not direct though. Like there is some steps that needs to be covered here. So let's go try to see very an intuitive approach and saying what those Moire fringes are and how they vary with strain. So what you have here on the left is a representation of your scanning grid in gray. In red, you have your atomic column. And in grid, this is the intensity collected in your ADF detector. That is just the geometrical overlap of a certain circular probe with the atomic column. So if you're on the atomic column, you have a high intensity, in between low. So if you see here, the P is relatively close to DC. We are here in the condition of undersampling. And you can see that following the periodicity, the Moire periodicity seems to be, larger, like, and following 5 or 6 atomic spacing in comparison to your crystal lattice here. If your crystal lattice has a certain strain, so you change, for example, the spacing here, you can see that this Moire spacing is changing in a certain manner. So in that case here, this was made bigger, the Moire sampling becomes smaller. You can so do the same in the vertical direction and you have both combined. So there is here an intuition, this feeling that the Moire signal is varying with the strain. But the geometrical link is not that obvious. It's become even more complicated when you, for example, consider a shear. So this is here like the same setup that we have before. In blue, you have the corner of the maximum intensity. And if we consider now like a shear deformation, so a little bit of angle now, we can see that now we have some inner feature that are coming inside, and we don't have like this nice squarish pattern that you have here. Only the two on the top are kind of kept, but all the bottom here, there are some intensity distribution with some inner frequencies that are appearing. So definitely this intuitive approach is not sufficient. We need to have like a more detailed theory to take into account of how the Moire fringes are changing with strain. And again, we're going to be looking at that in Fourier space, because the Fourier space is going to give you a very good way, a qualitative way of understanding what's going on. So this is a Fourier transform of the oversampled indium phosphide crystalline sample with two different sampling parameters. So this is a condition of high resolution STEM imaging. The idea here is to look at how those reflections are varying with the pixel spacing. And the general rule, the rule that we can see here is that when you increase the pixel spacing, the reflections are getting pushed away and getting closer and closer to the edge of the Fourier space. And that's exactly what is happening. Then until you don't reach the edge of the Fourier space, then you are conditioned of oversampling. The moment you reach the edge of the Fourier space, you become undersampled. So if we simulate that process, like for different pixel spacing, so these are the same 5 reflections used for the indium phosphide crystal structures simulated for a pixel spacing starting from 50 picometer to 250 picometer. So the number 1 is 50 picometer, and the number 50 is 200 picometer. So what is happening here? So let's take, for example, this O2 beam. So you are getting, the more you increase the pixel spacing, the more you get close to the edge. And now what is the undersampling phenomenon happening is bringing a shift here and bringing back your reflection back to the other side of the Fourier space. And you are continuing like that. Every time you reach one side of the Fourier space, you have you are appearing on the other side. So the 220 here appearing on the other side. Let's take this 113 example, going on the top, appearing on the bottom, continuing, reaching the side, appearing on the other side, and so on and so on. This type of process is predictable, because this is the typical effect of sampling. So this is possible to reconstruct using a prior knowledge. The reconstruction is very simple. All these elements that are shifted in one sense, you shift it back to the original position. So you make an extension of the Fourier space and bring back all these elements, so here, there, and you back to the area that is outside of the Fourier space, but that still should be there. So a little bit of prior knowledge is required, and this is here what the processing the processing is doing. So the software is doing that for you at the condition you bring a little bit of inputs, and this is here the complexity of the technique. Because then after, regarding the strain, the deformation, this Fourier space shift that is caused by undersampling is explaining absolutely everything that you see in this geometrical intuitive approach that we try. So the delta G that is representing the strain is present at the vicinity of the reflection. So what is happening is that whenever you undergo a shift, the shift is carrying the delta G without any distortion. And this is the key element here, which means that the delta G here that is either taken from the red spot or the green spot, the shifted one, they are identical and they are therefore GPA compatible. So you can use directly the GPA method. So that I won't go exactly to the detail of that, but to do this undersampled approach, this large field of view approach, because the delta G is absolutely identical. The only difference here is the definition of the reference. So here you can see no sample, you have nothing. Here you need to bring a small correction, this sampling matrix. So a small input that you need to add to be able to just go and use this undersampled micrograph at a large field of view. So if you summarize this process, again, same sample as before, the indium arsenic phosphide case that has been acquired in large field of view. The part that is important to do is just to acquire the electron micrograph. So experimentally, it's very easy because you are exactly in the same condition in the STEM imaging. The only thing that you have to do is to use a large pixel spacing, so low magnification, and a slightly higher dwell time. That's usually to give a good contrast between the Moire fringes. So here, then after you just mask 2 non-collinear reflection like we did in GPA before, and then this is so done in the Stemware GPA software, and then here we need to apply this correction. So this is here what is showing. You have, for example, so this is not the phase directly, this is the G. So the phase that is correctly, that is converted into a G. And then here those G, so M for Moire, C for crystal, needs to be corrected by this small correction. And this here, it requires an input from the user. So I won't go to the detail here, but that's here the complexity of that is to find those values to be able to do this correction. Once you have that, then after you just do like the classic strain map using the GPA algorithm, exactly the same thing. And this is what you get at the left. So 0 everywhere, as expected, except along the out of plane direction with the positive deformation in the middle. So simple experimental setup, but a little bit complexity in the processing. And that's what can be summarizing this type of method. Just to show you that this is working on whatever type of device. So this is here an LED device composed of aluminum gallium nitride heterostructures on the gallium nitride substrate. And you will, so without going too much into detail, but you can have the like kind of a similar strain maps. So conclude on that method. What you gain here is the gain is the huge field of view from 1 nanometers to a couple of micron. The sensitivity 10 to minus 3, 10 to minus 4. So I would say it's slightly worse than the nanobeam diffraction. And you have a resolution that is going from 1 to 20 nanometers, can be actually large. It's just an extension of the GPA method to large field of view. And it's a simple experimental setup. Regarding the limitation, strong impact of scanning noise. Coming back, that's the problem of STEM. The processing is not simple. That implies a reconstruction step, and it needs some user input. And the specification of the probe corrector is only valid for low field of view. So whenever you go to large field of view, you might be pushing the microscope a little bit on this edge, but I already confirmed that you can do a little bit until like 1 micron relatively safely, especially if you use 300 kV. And so let me just now finish on the last technique. So here, again, another level of complexity. And again, here, this will really need to be a justification in using it, which is Darkfield electron holography. And now the idea of doing this interference, so before we're just overlapping the sampling wave with the sample, now we're gonna just physically make the interference of the electron beam itself inside the TEM. So this is just an example here, that you take your the wave going into vacuum and another wave going into in vacuum, so just your electron beam. You put in between something that you call the biprism, that is acting as a beam splitter and recombiner just underneath. So by recombining, you can think about like just have a positive wire, the positively charged wire that is bending the K vectors of this electron beam on each side. And this bending, this difference of bending, you can see here, and this just changing the size of the lateral component, is just then after when you just do the mathematical equation, it's gonna bring this oscillatory component. And that's why you see those type of holograms in vacuum. That's what is possible to see by bringing this biprism in between. So by changing the potential of the biprism, you change the field of view and also the fringe spacing, you change the carrier frequency, this K prime, depending on what you want to do. So this is the way of expanding the field of view of your hologram. So how to do this? So technically, so this is the image of the Titan low base. This is where you put your sample in. The biprism is located here in the SI plane. So what you have access in the biprism is the voltage and the polarity. You can change to negatively charged, and this will also work. Then after, what is very important to use is those experimental parameters on the top. So here I just put Lorentz lens. We use the Lorentz lens in this type of setup because not because we want to have the objective lens off, but the idea is to increase the field of view. There is in this setup, so different from some Hitachi microscope, to have the larger field of view and a good overlap with your hologram, you need to go in this Lorentz mode. And after, you need to play with the diffraction lens to adapt the field of view of your hologram towards your sample. And that's usually the classic way of thinking about holography. You have a wave 1 that is going into vacuum and a wave 2 that is going through the sample. And by doing the interference in this process, you will bring again the carrier frequency, and you have here the phi s that is coming from the interaction with the sample. And so this setup will explain, is used like for example, look at electric field, magnetic field, or crystalline potential. So I won't go to the detail just for the sake of time. I'm just going to speed up a little bit. But what I just want to mention here is that what we are interested in regarding strain is the geometric phase. And I recommend actually to read that paper if you want more detail about this. The geometric phase is only visible in the diffracted beam. So this setup here is kind of insufficient, especially if you look at the primary beam. So we need to kind of tweak this a little bit differently to be able to see this geometric phase. In addition, we want to see the delta G, so the variation of the G vector. So putting this into vacuum is not that of interest, especially if you go in the diffracted beam, you will see the zero beam. So what we're going to be doing here is making the interference between two areas, one area that is strained, one area that is unstrained. The unstrained would have 0, the strained would have a certain delta G. Then to see the diffracted beam, you need to go into you need to select the diffracted beam. So to do that, we tilt the beam This is to put the diffracted beam on the optical axis. So that's the idea here. This is what we call the dark field imaging. Then we isolate the diffracted beam using an objective aperture to have only that. And then we put the biprism underneath to interfere the diffracted beam between them. So at the end, if you look at the interference between those two elements, all the other elements of the phase that is contribution to the phase cancels out, and you have only the delta G that is remaining in your hologram. So you can see that we are piling a little bit on this complexity. But at the end, if you just do two dark field holograms from two different diffracted beams, non-collinear, you can do exactly the same approach, extract the phase on the holograms like you've done in GPA, and you get your delta G matrix in the same manner as in the other techniques. The one point that is different is that we have no GRF available, because this K prime, this carrier frequency, is not dependent on G at all. It's depending on the potential that you use on the biprism. So the crystal structure and the lamella planes needs to be provided by the user. And here the calibration matters of your microscope matters. So this is a prior knowledge. And by adding that, then we come to the same equation again. So there are some softwares doing that. So HoloDark, this is a licensed DM plugin. I made like a homemade Python script, not that great, but that is gonna do the job. So if you want to do this type of technique, you can talk to me and we can see what we can do. But definitely there are less solutions because of like the technique is less popular. So going through relatively quickly, this is first an image in Lorentz bright field TEM. So typical settings that you will have here: relatively high excitation of the Lorentz lens, relatively high excitation of the diffraction lens. The objective lens is either turned off, or you can slightly excite it. This is what we call the dual lens mode. So it's kind of complicated way, but that is helping in adjusting the field of view. And the typical field of view you get is from 200 to 1 micron. Then after you have to, on top of that, go to the dark field tab, beam tilt your sample, so max 1.5 degree. You don't have that much room in the beam tilt in the Lorentz mode. Because then after the beam hits just the side of the column, and then use the objective aperture 10 or 30, like something that just isolated to have your diffracted beam only into the signal. This is a typical Lorentz dark field image of the 202 diffracted beam. And then you put finally your biprism on top of that to record those holograms. So you have two dark field holograms here, the 220 diffracted beam, the 002 diffracted beam, on our same sample again, indium phosphide and arsenic phosphide, indium phosphide. So just to comment quickly, the acquisition time that you have roughly is 10 to 30 seconds. Here they also put on the GIF CCD with a 10 EV slit to remove the electrons that are not contributing to the hologram. And also there is an additional sample tit to bring in two beam condition. This helps in having a more uniform intensity distribution and helps in having better contrast in your hologram. So you'll have to sharpen your eyes to see the fringes. So this is on the 220, there is no deformation. 002, if you look at well, you might see that the fringes here, they change the spacing and a little bit of their orientation. This is the indication that there is a deformation field. And here, for example, so on the 002, the diffraction contrast was good with the uniform intensity. On the 220, it was not that great. You see those dark areas, very difficult to find this two beam condition. So I might be close to an extension distance here. But at the end, you can get those train maps. And what is very, very interesting in those train maps, that they are extremely sensitive. You can see like the level of noise is one of the order of magnitudes better than what has been shown in the Stemware maps. So with a similar resolution, yeah, you can go down to the 10 to the -5. And the little dots that you see here are actually the carbon contamination that is coming from the STEM imaging I did before. There's amazing sensitivity of that. So of course, the limitation, very complex setups. You have the aberration from the Lorentz lens, there you have some tilt that is needed. That's all. Kind of we understood like what the limitations are, but then after you get a very, very nice train maps, especially very highly sensitive. So that's gonna be it for the presentation. I think I was long, so I don't know. So I will just conclude on what we talked about. So we went through a set of different methods, from high resolution to the diffraction and holography, going from high resolution to low resolution, but from poor sensitivity to great sensitivity. But also this is pairing with complexity. we started for something very simple and we got to something very complex at the end. So we talk about like the peak finding algorithm, geometric file analysis, the embed techniques of the 4D stem, and then after the holography, Stemware GPA and Darkfield holography. With my recommendation for a regular user is to use those diffraction techniques. And on the right, where I just put, is just the overall comparison between Darkfield holography, Stem GPA, and Stemware GPA, so that you can see here. That I would, so that, you know, the overall matches, but there are some differences that are non-negligible here. And those differences come from the strain relaxation phenomenon. So if you want, I can detail more in the discussion section if you want. But yeah, that here, I didn't put the diffraction data since I was not totally sure about the processing method, but this will be like cool then after to have what the embed will be doing. And that's it. I thank for your attention and I am open for questions.
Great, thank you, Alex. That was amazing. Just going through all those different methods of evaluating the strain and then providing like the pros and cons of each one. That was great. So there are some questions, and if you have more questions, feel free to put them in the Q&A during this time. So Farzan asked, if you go back to page or slide 11, could you explain a little bit more of the schematic?
Sure.
How did you draw the graphs, and are they a result of the simulations?
Absolutely, yeah. I went fast on that. So those are simulation results, final element method, mechanical simulation. So in here, we started with this global geometry that I just detailed here. That's the original geometry that is shown here. What you have roughly is this window is 1 micron by 1 micron by 1. So 1 micron by 1 micron, 100 nanometer in thickness. So then after this whole thing is 1 micron for the pillars, 3 microns here. And then yes, we just put an initial stress into that little layer. You see what you have in green. This is the indium arsenic phosphide layer that has been to put some initial strain. And then after we let it relax to see how it goes. And you have this bowing that is shown. So of course this is exaggerated. This is I think times 40. But yeah, this is like the final element method, mechanical simulation of this strain relaxation on this 3D object. Then here, it was just a cut to see just on the window region what was happening. And as you can see, the scale is now different because like the deformation on this window level is slightly lower. And what was interesting to see is that there were no deformation along the 110 direction. So the pillars on each side were maintaining the structure. And this was then after used to change from this 3D problem to this 2D problem. Because the problem of this final element mechanical simulation is the meshing. The density of the mesh was absolutely huge on that one. I think there was something like 1 million nodes. And even that, those nodes were not properly mapping the strain into the stress layer. So we find a way to simplify the geometry to have like a better description of the strain relaxation phenomenon. And if the person who has the question wants more detail on that, I actually posted on GitHub like the code doing this simulation using the Python package Phoenix. So I can maybe even answer in the chat directly. I will do that later. But like yeah, there is definitely some information that can be done there.
Okay, great. And then another question. So Rohit asked, is it advisable to do strain estimation on FFT/IFFT processed images?
Yes. So yes, absolutely. This is what the GPA method is based on that. So I would just my point will be here. Do you look at only on the FFT itself, because it is possible to see on the FFT itself already some aspect, or is it just like using this GPA approach where you just mask an area of the Fourier transform, then come back into real space and look at the phase variation of that? This is totally possible, totally possible. The one thing I will just comment on that, because this is a good comment. Regarding like this large field of view, This is, for example, the Fourier transform of that structure that we have on the left. And you can see the Fourier transform, how, we are supposed to have dots, but we are so sensitive to the deformation that we have some extension of that make now the Fourier transform looks with some structure. And this is related to the strain distribution into the in the device. But definitely, like Fourier transform base, they include all the deformation inside. Yeah.
Great. And another question from Rohit. Can you explain again how the reference is chosen in the case of strain estimation from high-res STEM imaging?
Okay, so this will be, so I will just go back to the theoretical aspect. So just to make it the point. So the initial, so I will answer in 2 steps. So first of all, here, when we think about the reference, this is what we have to keep in mind, is that we select one area that represent our original strain state. So if, for example, I select this area, I will have this lattice spacing and this lattice spacing, and also the angles. That's going to be my representation of my 0 strain state. So if you have the same lattice spacing, you will have no deformation. So if we go, for example, on this case, where you have this relax that is not in epitaxy on that, we will say exactly the same type of reference method. Here you will get a lattice spacing that is slightly larger, and you will get like a positive deformation. So if we go then after into GPA, for example, and then this will be in this case, okay. If I use the indium phosphide substrate as the reference, I will have here a positive deformation along the growth direction. But nothing is stopping me in taking the reference inside the INASP layer. And if I do that, the deformation is going to become 0 in the INASP layer, and it will become negative in the indium phosphide. So that's when you choose a reference, you arbitrarily choose that this area of that you have chosen has 0 deformation, and then after all around is going to be this delta G.
Okay, great. And just one note, I was sent, both Alex and I were sent actually a note from Colin Ophis, which is exciting since he, I think Alex referenced one of his papers.
Oh, yeah, that's great work.
So he just wanted to note, in terms of the drift correction, he would strongly recommend rotating the scan direction 0 and 90 degrees when collecting data for strain mapping. SmartAlign will work even better with the rotated images.
Yeah, to not have any bias regarding the direction of the crystal that you use. That is true. That there is this option in SmartAlign when you actually can rotate. Yes, yeah, completely agree with that comment. That to remove any biases regarding the scanning directions, that helps. Yeah, I didn't went to the detail of the SmartAlign approach, but definitely this is a good idea too. And I will add also to not have exactly the atomic column align along one scanning axis, also to tilt it a little bit off. Yes, definitely.